Good morning, everyone. So, welcome to week 12 of deep learning. So, as usual, today also I will be going through the concepts which was covered during the week 12. Then again, we will be solving some problems from the last year assignment 12 so that it will be helpful for you to solve the assignment problems. And if you have any questions or any doubts, please feel to ask. Okay. And today will be the last session we'll be having. Okay. So, yeah, let's get started. Okay. So this week it was mainly covered was encoder and decoder thing and something related to attention mechanism. So you are all very much familiar with the chat GPT or large language models, and the main architecture behind such a large language models are just transformers, which are attention based. So this week lecture, this week content was mainly inspired that what our attention is, how to model this different kind of a task. Means you give input as an image, asking what means describing the image, video captioning, okay, language to language translation and all. Okay. So yeah. So first of all, we'll be seeing what are encoders and decoders. Encoder and decoders. Okay. And then we'll be seeing some of the application. So I won't be going into the depth. I will be just describing that how it happens. Okay. If further, I hope that you went through the lecture materials. Okay. So it has been very clearly described that how to model different kind of a task using encoder decoder kind of an architectures, applications. Then I will be covering something attention mechanism. So not fully the same kind of an attention which is there in transformer is covered, but the concept wise it remains the same. Okay. Okay. And lastly, the problem solving. So these all things we are gonna be covering this week. Okay. And if you have any doubts, just feel free to ask it. So first of all, let's revisit that what was covered during the previous week. Okay, so as of now, we have covered quite a lot of stuffs. Okay, like week 11, we covered about the LHTM, RNN kind of an architecture. So this week is just kind of a continuation from the same point we left, but kind of a new architectures and new ways of formulating the stuff. Okay, so the thing we are modeling. Okay, so for example, sentence completion. My name is something. Okay, so this is just a auto completion. So this kind of a task, what you are doing is basically you are taking a previous words and try to predict the next word. Okay, and predicting the next word is not a straightforward. It means it is not very much straightforward because there can be quite a lot possible number of words which can come. Okay, so the main purpose of this kind of a task is we want to know what's the probability of having the next word. So we are kind of doing classification task. We but the classes are very large numbers. The vocabulary of the classes are very much large. It's of the size, out of size. Okay, a number of words in the dictionary. So, for example, as I mentioned that Delhi is the capital of India. Okay, Delhi is capital of dash. Okay, so that's kind of a classification task over the vocabulary size. But just using all the past information to predict the next word is not the means. It's not quite easy task. It's a tedious task. So as you are reading a book, okay, in chapters, any book, okay, it has been organized into a chapter. Each chapter has a certain information. Okay, next chapter is independent. It assumes the information you are already familiar with, a bit, okay, context, okay, and but it's completely out of means to have a new, for example, new story in the new chapter. It just you just need a very much little bit to know from the previous chapter. Actually, it's completely not dependent on it. So whenever you are asking ChatGPT very big questions or just copy paste a book or something like that and ask question, it hallucinate. It does not know. It just predicts something nonsense basically. Okay. So sometimes you don't need to have the other information whole from the starting to the last point of a time. Okay. So actually what we are doing is we are trying to predict the next word. Okay. Which is our max probability of y of t given the information from y1 till t minus 1. This is a okay. So this is argmax. Okay. Argmax, the argument which makes this probability maximum. That's what we are asking. So we have been given the information from y1 to t minus 1, the words. We are trying to predict the next word yt. P means the probability. That is the summation over all the vocabulary of P of T. Y of T is 1. Okay. Argument max is what value of Y of T. This value is maximum because we want to give the in classification. Okay. We want to classify as a dog or a cat. Okay. The maximum probability, whatever the model is giving, we are going to be taking as a prediction. Okay. Because that's the truth basically. Okay, otherwise for random city you can just flip a coin with the higher probability you'll be getting the correct label for it. Okay, but in the end we want the higher probability for the correct next word. Okay, and that argument we are going to be predicting it. Okay, so I hope this notation wise it is clear what is. Okay, so this was happening in RNN. What we were doing is we had certain something like this. Okay, we were having UVW matrix. Okay, so it was UV and there was a looping of W. Input was XT. It is given ST, and we are gonna predicting YT. So the some looping mechanism was happening, and this was the in context which ST gonna be used in the ST plus one as well. Okay, so like this with auto regressively, we can run this sequence arbitrarily many times until unless we reaches the end point. Okay, so this is how we were modeling the normal auto regressive because this kind of a task I'm speaking. Okay, it's a auto regressive task because the next word what I'm speaking is completely dependent upon the previous words what I have already spoken. Okay, and initially, the word we assume this as not to be some random which may random initialization, and we just ask model to run that as well. Okay. So this was the basically the task we were carrying it out. Okay. So I am at home today. So initially I will be just giving a random noise go as a token. So I will be describing few special tokens, starting token, end token. Okay. Because this token tells me that I need to stop after this point, the dot, basically in the English sentences. Okay, because you cannot have a infinite context without any stop page. Okay, because every any sentence you can have of maximum 20 then 30 then that's the maximum you can have. Okay. So basically we were doing this classification task. Okay, and the output as it's a classification task. We want a probability. Probability, the summation should be sum up to 1. And each and every element should be positive. Okay. So that's a summation over this summation of the probabilities. Okay. So for that, we have already seen we have defined something softmax. Okay. So what is a softmax? Basically, we defined an operation softmax which take a vector e to the it raises element e to the power that vector divided by summation over all the vectors. Okay. That's how we have defined the softmax operation. Okay. And like this, the softmax operation was giving us the probability distribution, which is a valid. Each and every element is positive, and the summation over all the across all the element, all the classes sum up to one. Okay. So how do we train such kind of a model? So we had a large amount of corpus, okay, from Wikipedia or any internet. You'll be getting large amount of data. Okay. So the model, this is the auto-regressive task. Okay. We were using this kind of an architectures where we're defining U, V, W, BC as our parameter. BC, for simplicity, I have avoided the bias terms. Okay. And we were predicting the next word based on the based on the previous information we are having, plus some context from the starting to then. That's a compact representation of the prior informations. Okay, because that is needed. Okay, because the next word it is dependent upon previous, but also on the context I'm trying to define the priors. Okay, and then we were using the loss, unlike the same loss, the cross entropy, which is L theta minus log of probability of yt is equal to Lt given y1 till t minus 1. Okay. So this is the normal cross entropy loss we were using to train our model. Okay. And we were using a previous predicted time step information try to feed forward it. And we saw something as back propagation through time. And back propagation through time was unstable. There was a vanishing gradient problem, exploding gradient problem. Okay. To counter it using the LSTM and created recurrent units, okay, where we defined a special type of gates, reading, writing, okay, for getting gates, okay, and we were learning it, and we saw that the vanishing gradient problem was much more, means it, we avoided that problem. And for the exploding gradient problem, there was not a great solution for that. But to model that exploding gradient problem, we just clip the gradients. Okay. But auto-regressively training any model is computationally not efficient, actually. Efficient in the sense because, for example, you are having a lot of, because the corpus strength can be a very bigger in size. Okay, article, for example, any story you are taking. And in the story, for the model to run the parameters, okay, we were feeding inputs, and auto regressively we need to get the output. And this back propagation through time, the as the context length increases, the back propagation through time is the computationally inefficient method. Okay, so that's why people came up with this transformer kind of architectures, and that now using the word because of it's able to parallelize the computation and at once only getting the output at once. There was not a back propagation through time. Nothing is there in the transformer like this. Okay. At one go, you can compute the output, and to update the parameter, you don't need to again back loop through the time. Okay. So RNN, you can think it of as the special kind of operation we defined was ST, which was the intermediate latent information till the time t, and it was defined in the RNN, which depend upon the previous time step we were having, and also we were using xt, the current input. So this is kind of, those who are familiar with dynamic programming or recurrence, it's kind of a recurrence which is happening. We are trying to combine the information of the previous time step and the current whatever input is coming and try to produce the next intermediate stage. And that's what we do in the dynamic programming itself. Okay. Suppose in the normal array is given, I want to sum up. Okay, the array length can be very much bigger. And suppose if I give you particular index, I ask you what gave you starting and ending index. I ask you find this thing, the sum of elements between this starting index and end index. The normal brute force method you can do is just go and use the for loop, go element by element, add from the starting index to the end index. But that's not computationally efficient. Okay, the more efficient way is just prefix sum. So the normal prefix sum, what we do is suppose 1, 3, 2, 5, something is there. Okay, I want to know the sum between this element and this element. So normally I can use the for loop. Okay, but this is not a best efficient way. As my array here is a small, then it's okay. This is just okay, but it increases means 10 to the power 5, 10 to the power 6, something like that. Then this is not okay at all. Okay, so what we do, we find that we define a prefix sum. Prefix sum, it will store the sum till particular point of time. Okay, so here it will be 1, 4, 6, 11. If someone asked me what's the this thing, sum of elements from starting index 0, 1, 2, 3, from starting index 1 till 3, it will be just index this 11 minus 1, just index previous one. What was the summation up to that particular point of time? And this is just order of 1, because you just need to pick two elements and just subtract, get the answer. No for loop, it's very much efficient in dealing with. Okay, and this kind of a thing, prefix sum, is very much common in competitive programming or DSA they teach. Okay, so the same question arises here as well. Okay, as the next time step, the latent representation depends upon the previous time step, this current time, input. And this back propagation through time, as my context and increases, it's not efficient at all. We are not using GPU to up to its full potential. Okay, the GPU is very much useful when you want to in a very much large amount, so means again and again. Okay, and that's one thing. We are doing the same operation again and again. Okay, but the thing is this time constraint we are having. Okay, so to remove this time constraint, we want, for example, the conversation. Okay, so that kind of operation become very much easier. So now you might have seen that we want to generate a sentence given we want to generate the next word given the previous word. Like that, you can also describe a different task. Okay, suppose if I give you an image, okay, and you want to describe what is there in the image, what's happening. Okay, for example, a man is playing a cricket. Okay, then how to model such kind of a task? Because input is the image, output is a text. Okay, and in the text also we know that it's of the vocabulary certain size is there. Okay, so how can we model such things? The question is that. Okay, so the normal thing in the architecture, if you see initially the x naught, okay, we can give as a we can use an image, we can pass the image with the CNN kind of an architecture, which we extract the meaningful abstract means features. Okay, basically using that feature, we are gonna condition in the initial input, we are gonna pass that's the feature and asking our model to predict the next word. So that's how we can model this kind of a task. Okay. So they are so basically this kind of a task more it's more like conditioning. Okay. Conditioning in the sense we want to generate a sequence. Okay. But there is a prior information which has been given. So in this case, it was the input image. We want to generate a sequence condition on this particular input image. So this kind of a thing you can see as a conditional sequence generation. Okay. So you can also think it of as, for example, I am going home. Okay, मैं घर जा रहा हूँ. This to sentence from different language to different language. Okay. So this kind of a translation task, if you see, if I have already know मैं घर जा रहा हूँ, and I ask you to translate to English, I am going home. So using मैं घर जा रहा हूँ is the prior information you already know. So you want to use this conditioning and try to generate a sequence task. Okay. So how can we do such model such things? Okay. So that's the thing. Basically, initially to generate this RNN, the S naught or this X naught, you can use this conditioning variable and then try to generate the whole sequence. So that's the straightforward method, okay, of conditioning. And there can be another way of conditioning, okay, at each and every point of time in RNN. X of t, S of t, Y of t, okay. We already have certain information which I suppose I represented by Z of t, Z, okay. This conditioning variable, after extracting the image, you can just concatenate it with this vector at each and every particular point of time. So it's like I already have certain information. I want to utilize that information in my model. And this kind of a task is more like a conditioning. Okay. P, Y given something X. Okay. So you want to model P of Y given X. Okay. This is same as saying that P of X given Y, P of Y divided by P of X. So it is by the normal base rule I'm using. Okay. So this we are modeling, we are just concatenating it with our input variable and try to predict the next variable. Okay. So it's the same thing what we want. So these are the two kind of an option you can have whenever you want to model something conditioning. Okay. So for example, you might have seen this thing nowadays, this text to image generation model, okay, on a Hugging Face. So there you just give the image, you also give certain text, okay, and just try to ask it to edit a photo, make it look like a cartoon, kind of a different task you can have, okay. So there also the conditioning happens in the same way. We take our image, we generate embedding. We take our text, we have our embedding. The text embedding, the image embedding, we just try to make a attention map, which I'm going to cover later. And then using that as an initial conditional variable, we just try to generate whatever the task you want to convert into a cartoon image or in such like that. Okay. So this is more kind of a multi-model thing. Multi-model in the things in the sense we want to take a different kind of a data. Image is of a different data type. Language, we are much more flexible to run the embedding ourselves. Okay. So this is kind of a thing. Okay. For the application, there, as I mentioned, two application we already have seen. Image captioning. We can also have a video captioning. Okay. We can have a translation task. Okay, from one language to other language. Okay. We can have a auto completion. Like this kind of a lot of tasks can be there. Okay. So you can use a RNN kind of an architecture. Okay. Along with that, if you are imposing an image as a conditioning variable, then you can use the CNN to extract the variable, then conditioning it. Okay. So that's our view of the application of this kind of a thing. Okay, online. So like this, as in this course, you already got familiar with a lot of concepts. Okay, so one thing which I will be suggesting you is that go and implement this and see it yourself. Then only you can conceptualize what you have understood throughout this material. Okay, because as of now, you just already know that this is happening, that is happening. Okay, but it's great to see what's in the real time by coding itself, how you're conditioning it, okay, how you are making a vector, certain vector shape and all. Okay. So those who are interested, pick one image captioning, for example, as one of our project. You can find a lot of it data sets on a Kaggle or anywhere. Just use the data set, try to build a model and see how it's performing. Are you able to grasp the concept? Okay. What's the best way of conditioning? Okay, just starting, just passing it or passing every time with the same thing. Okay, and unlike the loss is going to be remaining the same, the cost entropy. And this model we are going to be using means you can take using any means optimizers. Okay, it's better to use the Adam kind of an optimizers. Okay, because Adam works where no one means no other optimizer works actually. So Adam is the way to go kind of an architecture. And also you can make a chat box image question answering, where you can pass image and a question, and you want to generate certain answers. That's also one kind of application you can have. Okay. And also the video classification task. Okay. So these are certain kind of thing which, and also when you are coding, you will be just understanding how much means just getting to know the concept. It's okay, but how much time you just take to just run the codes. Okay, what's the computation? Okay, you can write any brute force method and it will be working, but the amount of time it is taking to run, you want to maximum minimize that effort. Okay, so now let's see about the attention mechanism. Okay, so the one fundamental drawback you might have seen every time, for example, this transition decoding we were trying to have a compact representation of the hidden information. Okay, S of t, and using that S of t, then we were using RNN to decode it. Okay, so the RNN, it was predicting y of t, which is just RNN, which take X of t, and also S of t, the compact representation of the encoder part, and also the latent representation. Suppose for that I represented Z of t. Okay, so this kind of an architecture we were having. Okay. So, but the thing is, S of t we were using as a starting point for decoding. Okay. So what's the fundamental drawback? Okay. So for example, simple example, if you take language translation from Hindi to English or English to Hindi. So suppose मैं घर जा रहा हूँ. Okay. There are total 5 words. I am going home. There are 4 words. Okay. So to decode it, okay, घर, I know it's represented as home. Okay. जा मतलब going, मैं मतलब I. Okay. So there is a one-to-one mapping. Okay. I am going home. Okay. मैं घर जा रहा हूँ. So if you see this thing, the home is created with this घर. Okay. I is मैं. Going मतलब जा रहा हूँ. Am going. So this is related with जा रहा हूँ. Am going. Okay. So, and it is not very much sequential actually. I already know this. I want to translate to I am going. So initially I was having a compact representation of this using S of t. And using that S of t, I was decoding using RNN. Okay, it was giving me I am going home. But this is okay. But aren't we using any information? I know that this I is dependent upon this whole information, as well as it also depends more on the man, the conversion. Okay. So how can we model such thing actually? Because I know that to decode this word, this her word is important. This whole sentence that is S of t, but this ghar embedding in between is also important for it. Okay. So how can we model such things? So that is where this attention mechanism will be coming into the picture. So attention means I am gonna generate a matrix, okay, where suppose the output is 4 and the input is total 5. Okay. Now what I'm doing is basically I want to learn a map this matrix, okay, and I am going home. मैं घर जा रहा हूँ. Okay. So now what is happening is that I want to run a mapping that how much this word is dependent upon this. So the more it depends, the more it will be darker, the more weightage. Okay. Girl, this word. Okay. So like this, I want to run the mapping. So, but the thing is, this mapping, I know as a human, I already know, but to have this kind of a mapping is almost impossible task. Okay. So to learn such kind of a mapping is kind of a very much tedious task. Okay. So how can we make it much more easier? Okay. Can we ask our model to learn this thing as well? So that is what this attention. You can call it as attention map. Okay. And it is having the same concept as in the transform. We are having a self-attention, cost-attention there, which was not covered in this. But those who wants to know, just go and type attention is all you need in the paper. You'll be get to know, okay, that why they are doing a particular kind of an operation. What's the purpose of doing that operation? How they want to capture the in-between correlation between the two sentences. Okay. So they use the self-attention and the cross-attention. The concept wise, it's very much similar, but you can just see it. Okay. So the drawback we were having parallel is the encoder reads the sentence only once and encode it. Okay. One compact representation. At each time step, the decoder uses its embedding to produce a new word. That was what was happening. Okay. Now, as this human also, we don't translate in such a way. We just if I ask मैं घर जा रहा हूँ, I ask to decode it. We be just first of all mapping that man is happening. So that's kind of a more motivation behind this model. Okay. So how can we try to produce the next word focusing on particular kind of words? Okay, which we already know. So essentially, at each particular time step, we need to come up the distribution of the input that to decode this word, how much importance this out of this all word, which word is more important. Okay. So to model this thing, as I mentioned, we want a model to learn this as well. So how we can model such thing is, so in Coder, we were having something like the 5 words are there. Okay. Okay. Now, what I wanted to do was basically this encoder मैं घर जा रहा हूँ, we were generating a common embedding we were using for decoding it. Okay. But in between this representation is also valuable for decoding it. Okay. So suppose how much this word is helpful to decode this I. So to model this thing, I am going to describe one more operation, which will be taking this thing and will forward it to be this thing. Okay. So I'm defining the weightage of this thing, alpha 1, 1. Okay. Alpha 1, 2, alpha 2, 2, alpha 3, 2, alpha 4, 2, alpha 5, 2. So this 2 means in the second word and I want to decode it. And this one represents the current embedding. Okay. So this alpha denotes kind of a, you can think of as a probability distribution that I want to know that out of this all words, which word plays a very much important role in decoding the next one. Okay. So of course, this kind having this kind of prior information is tedious. We don't have access actually. So we are going to be asking a model to run itself as it is generating an embedding. Using the embedding, we are going to ask us to run this coefficient as well. Okay. And this coefficient you can see as a matrix because this 5 and the summation across I is there, this will be 1. Okay. So this is what one was the way of encoding the information. Okay. And this information, as we don't have already access to this map, we are going to be asking our model to run this model, the thing as well, this coefficient to decode it. Okay. So like this, we are going to be combining based on this plus this coefficient plus the embedding and using it to decode the particular word in the output decoder part. Okay. And the same thing get extended in the transformer as well. Okay. So that is not covered. Those who are know, they can just refer the paper, the first paper that is attention is all you need. Okay, these people you can refer. Now let's start solving some of the problems. Okay, problem solving. Okay, the first problem. If we make a vocabulary for an encoder decoder model using a given sentence, what will be the size of our vocabulary? Okay, the sentence. We have given one sentence. Okay. Encoder decoder models are used to perform language translation tasks. That's a sentence. Encoder decoder models are used to perform language translation tasks. Language translation task. I have just omitted in the small words. Okay. So total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 words are there. But we also have a 2 words more. That is a starting and end. Go and end word. Okay, that's the token. So total we are having a 12. The vocabulary source for this sentence is 12. 10 is the number of words plus 2 starting and end. Okay. Now, We are performing a task where we generate a summary for an image using encoder decoder model. Choose the correct statement. LSTM is used as a decoder. CNN is used as a decoder. LSTM is used as an encoder. CNN is used as an encoder. Yeah. So image captioning we want to do. We have an image. We'll be using image. Okay. So image will be modeled using CNN encoder. And to decode, we are going to be using LSTM decoder. Okay. We are performing the task of machine translation using a encoder decoder model. Choose the correct representing the encoder model. So basically, encoder model, machine translation we are doing using encoder decoder, and we want to mathematically represent the encoder. So we use RNN cell. Okay, that's one thing. And in RNN cell, the S naught is dependent upon the previous time step. Okay, so the choose the equation. So S naught is, so the correct representation is S RNN, and it's HT minus 1 X of IT, X of IT. So this S naught is the starting point for the decoder in the machine translation task. HT is the compact representation we are having, and this X is the particular instant we want to decode. Okay. Now, fourth question. We are performing the task of image question answering using the encoder decoder model. Choose the correct equation representing the decoder model. Okay. So in the decoder model, so in the image, what we are, the task is image question answering. Okay. So we are trying to probability of Y given Q and L. Okay. Question and the image. So this is the two conditioning variable, and that is dependent on the softmax. Okay. Softmax VS plus D. So that's the normal answer, I think. So the task for our output is coming from a fixed dictionary. Hence, we need to select a word with the highest output probability, and that is done by our encoder model. If given we are task performed using encoder and decoder model, select the task for which RNN of the CNN model should be used as an encoder. Okay, we are doing the RNN using the tasks encoder and decoder. And the question is, we'll be using definitely the RNN, okay? But CNN time kind of a model is used as an encoder. So which kind of a task? Image question answering, image captioning, video captioning. So we are going to be using video captioning. The encoder will be video captioning. Okay. Because there we don't have any text. We just want to encode the information at particular frame. Choose the correct statement with respect to attention mechanism in encoder decoder model. Attention mechanisms can't be used for images. Pause. It can be used. Only important feature get high weight in the attention mechanism. That's true. Okay. So in the attention mechanism, just remember the input feature, the one with the higher weight gets much more, what I say, much more weightage. Okay. So that's the common theme of using attention mechanism. Seventh question. We are given a task where we have to take input some sequence of sentences and produce a sequence sentence as an output. Which of the following model will work best for this task? inputs some sequence of sentences and produce a sentence as an output. So it's just a hierarchical encoder decoder network because we are going to be having a lot of sequence of a sentence. Sentence is also a sequence of words. So we are having a sequence of a sequence. So that's a hierarchical encoder decoder network. Okay. We are using a hierarchical encoder decoder network for the document summarization task. What is the number of levels at which we need to implement the attention mechanism? Okay. So just I'm again repeating, we are using the hierarchical encoder decoder network for the network document summarization task. We want to use hierarchical encoder decoder network. We want to summarize the documents. Okay. What is the number of levels at which we need to implement the attention mechanism? Okay. So the attention mechanism is used for combining the representation of the word in the given sentences. Okay. And as the same sentences is getting input for the decoder, so total number of is in that encoder at as a decoder. So total two we need to use. Okay. We implement the attention mechanism for image for an output of one layer of CNN. Which layer output should be used to implement an attention mechanism for the best result? Okay. So for the attention mechanism, CNN layers are the best for the attention because it contains the spatial information for the particular image. Okay. So it's just CNN layer. Select all the application of the encoder decoder model, video captioning tool, machine translation tool, image captioning tool, textual entertainment tool. So all the tasks which are there given are can be modeled using encoder decoder kind of an architecture. So that's it, guys, for the today's session. Okay, I hope you enjoyed the course material and the session. So if you have any questions, okay, feel free to just put it on a YouTube or just reach out to me. Okay, thank you, guys.